All right, section 3. First off, how many of you watched the video in this section? No? Okay, then I'll take time in class to go through what he talked about in the video. If we don't continue to watch the videos, then we can just put the class back where we talk and watch videos and I explain things all period, and then you guys can work on web work and stuff on your own at home, back to kind of the traditional math class, if that's what you want to do. I'm hoping by putting material on there that you're kind of getting a good understanding of things before you walk in, that I can just fill in the gaps and then help you with work during class. But if you'd rather work on this stuff at home and have me talk all period, then I can do that too. So I'll go ahead and go through what the video did and spend, it'll probably be most of the period, on the number e. We'll have a quiz on Monday on 1, 2, and 3, and then we're going to start logarithms then on Tuesday. Okay? So there's a number, like pi is a number. It's not like pi, but pi is a number. There's also a number called e, and it's actually on the calculator. Do I have one that works here? If you look at, there's two places for it. If you look at the natural log button, right above it in blue, do you see e to the x? And then do you see another letter e right above the divisor, or the division sign? So look at the natural log button. Right above that, there's an e to the x. And then right above the division sign, there's the number e. Do you see that? Okay. You guys see that? Yeah. Okay. So this actually, even though it's a letter, just like pi stands for 3.14159 going on to infinity, e stands for a number. And it was actually discovered by a guy named Bernoulli. And if you're in an engineering interest field, you're going to learn more about Bernoulli as you go into your college classes. But a guy named Euler, and it's spelled E-U-L-E-R, but pronounced Euler. A guy named Euler actually named the number e. And so he writes, it's called the Euler number, or the natural number. But Bernoulli really was the one who founded it, Jacob Bernoulli. I'm not sure how that works when you get to discover a number and someone else names it, and now it's called his name and not yours, but that's what it is. It's called the Euler number. And the way Bernoulli discovered it was, let's just pretend we're starting with the equation that we've been working with, which is this one. And yesterday we talked about if we change the compounding to something other than annual, this formula becomes this, right? Where n stands for how many times it's compounded in a year. Okay? So we're going to go through this, and maybe I'll give you guys a calculator too. You could do it in groups. We're going to go through this and just play around with a scenario. I'll just give you, you've got one, I'll give you one, and you can work together. So let's talk about a scenario where the principal we start with is $1, and the rate of return is 100%. What does that mean after a year? What happens to that dollar? You earn $1, so it doubles. So if the rate of return is 100%, that's the same as saying you're going to double your investment every year. Okay? So we're going to call the rate equal to 100%. Okay? So this formula changes. I don't have a p anymore because p is 1, right? So I just have 1 plus r raised to the t if it's an annual compounding. And the rate is 1 because I change 100%, move the decimal over twice, right? And that number goes in as 1. Okay? So if I'm going to talk about, let's just do everything for 1 year. So in year 1, actually we're going to do everything. So if n is 1, meaning it's annually compounding, right? The amount I have after 1 year is $2, right? So what if I said I want it compounded quarterly? What is n? 4. So someone figure out how much I would have after a year if my dollars compounded monthly at 100% rate of return. I'll just grab a couple more. So I'm going to wait until someone can give me a number of how much I'd have after a year if it's compounded quarterly. $16? So I'll put it into this equation. 1 plus, this time I have 1 over 4, right? Raised to the 4th. $1.25. I get 2.44. Did someone else get something different? Okay, so if I just had it compounded annually, after 1 year I have $2. Compounded monthly, which I'm still getting 100% over the course of a year, but they're just paying me my interest every quarter, and so that next quarter I'm getting 25% of that next quarter, but that quarter is now more money. So you can see already why more times compounded in a year, more money you have, right? Let's talk about monthly. Am I really out of space? Monthly would be 12, right? So how much money would I have after a year? If n is 12. Looking at the formula is 1 plus 1 over n raised to the nt. And t is 1. So it's just raised to the n. So what do I have if n is 12? $2.6. Give me a couple more decimals. 1.3. It's continuing to improve my profit as I continue to increase that compounding. Okay, what about daily? If it were daily, n is 365. What'd you get? 2.71. Yep. 71456. I get that. What would I do to n? So right now I have 1 plus 1 over 365 raised to the 365, right? How would I change this if I wanted to do it hourly? Compounded hourly. What would I have to do to 365? Multiply it by 24, because there's 24 hours in every day, right? So to do that, 1 plus 1 over 365 times 24, that's a times, raised to the 365 times 24. Someone do that one for me. This is a times 2 here. Are you working on this, Bo? What's that?
2.98.
I don't think that's right. 2.718. That sounds a little better. It's continuing to increase, but it's not maybe increasing at the same rate. You know, it really jumped from here to here. And now the bigger I'm making n, I'm still seeing an increase, but it's not going up quite as fast. What about minute? Every minute. So that would be 1 plus 1 over 365 times 24 times 60, right? Raised to the 365 times 24 times 60. What do you get there? Same thing as the last one? Maybe give me a couple more decimal points. Oh, don't do this to me. $2.7182 something or other, right? 279. Okay, and you can kind of see, I could go, this was minutes. I could do it times another 60 and get seconds, right? What do you notice about this number in the denominator? It's getting bigger and bigger and bigger and bigger, right? So what Bernoulli did is he said, I want to figure out, and he had to use calculus for this, which I'm not going to teach you that, but I want to figure out what this number approaches as this goes to infinity. As it gets bigger and bigger, and I'm continuously compounding. I'm not doing it every second. I'm not doing it every millisecond. I am literally continuously compounding. And it's interesting. You guys do second and then the number e right above the division sign. What number pops up? Nothing? Second e. Enter, sorry. 2.7182818828, and it goes forever. It never ends like pi. But it's interesting because this is what this number is slowly approaching as I get bigger and bigger and bigger compounding intervals. It's approaching this number called e. Okay, e is actually a number, and it's between 2 and 3. It never repeats. And you're going to use the number e anytime a word problem has the word continuous in it. If it's going to be continuously compounded, they don't tell you compounded monthly, weekly, daily. They're telling you it's compounded continuously. You will always use the number e. Okay, so you're going to use the formula that we worked on yesterday for any compounding frequency except continuous. If it's continuously compounding, the formula you will use the principal, or what you start with, the number e raised to the rate and time. Notice there's no n. There doesn't have to be because n is continuous. Okay, so if you have you've got an interest rate problem and they say it's continuously compounded, you're going to use this formula. If you have population growth and they say it's continuously growing at this rate, you're going to use this formula. If you have a radioactive decay problem with an isotope that's continuously compounding it or decomposing, if you will, at a certain rate, you're going to use this formula. Okay. Let me do a radioactive decay problem. The rate of radioactive decay of radium is modeled by this function. R equals P e to the negative, and it's 0.00043. Why is the negative there? If you have a negative exponent, What does that tell you about whether it's growth or decay? The negative exponent actually makes this that, right? To this rate. And remember, E is the number. It's 2.718 about. So if I have 1 over that number, isn't that number here less than 1? And if that number is less than 1, we know it's decay. Okay, so if I have a negative exponent and the number is greater than 1 to start with, I know it's going to be a decay problem. And it makes sense. Radioactive material decays. It doesn't grow. Okay, so it tells me that radium is modeled by this function. And there are 698.9 grams present after 5,000 years. After 5,000 years. The question is, how much did it have 5,000 years ago? What did it start at? So what number are we looking for in this equation, A or P? P. P is the amount you start with. A is the amount you end up with. They give us A. They say there's 698 grams 5,000 years later. How much did you start with if it decays at this rate? What's this rate equal to, percent-wise? 0.043. Remember, you always have to move the decimal place to over to put it in the problem, but this represents 0.043%. So this particular piece of radium, 5,000 years ago, was decaying at a rate of 0.043%, and today we have 698 grams, and we want to figure out what we started with. We're going to use this formula, plug in what they give us, so we have, after 5,000 years, 698 times 5,000. Okay, when you're raising E to a power, the easiest button on the calculator to use is that first one I showed you, which is right above the LN button. If you want to just put E in an equation, you can use the one above the divisor, because that just plugs in E as a number. But if you're going to raise E to a number, do you notice how the LN button, the function above it, has E to the x? So I'm going to take, I have to basically divide this by this number, right? I'm going to put that in the denominator and that over here. So what I'm going to do first is go ahead and solve for what this number is. So I'm going to say e to the x, and it automatically does e raised to parenthesis. I'm going to put in negative 0.00043 times 5,000 in parenthesis. And enter, and I get a number, 0.11648, so on. Everybody get that? So you're going to have to know how to use these buttons to do problems in this section. Now I'm going to type in the number 698 in the separate line, 698. I'm going to hit divided by, and now I'm going to hit the blue second and answer where the negative sign is. And that will pull in that 0.11648 to the denominator. Hit enter. That's how many grams of radium there were 5,000 years ago. 5,992.2 grams. Once we've learned logarithms, we're going to be able to solve a problem like this where they ask us after how many years will it have, what's the half-life? We'll be able to answer that question. What's the half-life of radium, given information? But we're going to have to use logarithms to do that, so we won't know how to do that until next week. For now, what you need to know is this is the formula you're going to use when you continuously compound something. It's going to have a negative here if it's decreasing, if it's a decay. It'll be positive if it's growth. But you will not use this formula if the problem has the word continuous in it. I've probably said it 3 times, and I guarantee on a quiz, someone's going to use this formula with the word continuous in a problem, and that will get you the wrong answer. You must use this formula for a continuous word problem. Okay? Any questions on section 2? Actually, let me go through the textbook check real quick. The equation below can be used, is this the right one? Yeah. To determine a final amount given the beginning balance, interest rate, and compound frequency. If an investment is compounded monthly, this is the wrong one. It would help if I picked the wrong one. This is what we did yesterday. 8.3. Okay, the number known by the letter E is called the natural number, or, yeah, Euler. It's pronounced Euler. It looks like Euler, but they pronounce it Euler. Euler number. So E, the letter E, is called the natural number or the Euler number. The number E was discovered by Bernoulli by increasing the blank in the equation. What? What did we do to find E? We just found E. We spent 15 minutes finding E by increasing what? Compounding periods. We started with an annual period and we went monthly. We just kept increasing that compounding period to find E. If we have this equation, 1 or y equals 2 times 1 over e to the negative x, this would be growth or decay? It's growth, actually. This number is less than 1, that's true, but the negative flips it. And by flipping that number, it becomes greater than 1. And if that base is greater than 1 and you have a positive exponent, it's growth. I don't know why I have extras here, but E is used when a problem calls for continuous compounding rather than annual, monthly, etc. True. And then finally, you possibly will see some problems where you're going to have to simplify, where E is the base now instead of 3 or 7 or some other number. Remember, E is just a number. So as long as the base is the same, all of the rules we've learned on adding, subtracting, multiplying, raising exponents to exponents, all of those rules still apply. So if I'm going to simplify this problem, I have e to the negative 3 and e squared. So what is e raised to if I multiply those together? What do I do to the exponents? You add them. Negative 3 plus 2. Negative 1. Is 2 raised to the negative 1 or just e? Just e. So if e is raised to the negative 1, that negative flips it. So e becomes the denominator with an exponent of 1. So the answer is 2 over e. Right? So you're going to have to continue to be able to apply the rules that we've already learned on exponents when dealing with the number e. Okay? No questions on yesterday's web work that's due tonight. You do have a question? What's one of your questions? This is number 1. The population of the world in 1987 was 5 billion, and the growth rate was estimated at 6%. They give us the formula. A sub 0, that's how you say this, A sub 0, is many times used to stand for initial. Sub 0 usually means initial. Okay, so instead of a P here, they just said A sub 0, but it means the same thing. It's what you start with. And here we start with 5 billion people. So that's A sub 0. And the growth rate is 5 or 6%, which if I'm going to put it into R, I've got to put it this way, right? Assume the population follows this growth model. Find the projected world population in 97. Well, we started in 87. 1987. Oh, my goodness. 1987, and we end in 1997. How many years is that? 10 years. So that's T. I've got everything I need now to solve for A. Right? I just plug everything in the calculator at this point. That help? Okay. There's lots of population problems. There's some interest rate problems in this section. But they all should be using this formula or this formula if the compounding period is something other than 1 year. Okay, and remember, if it's a decay problem, this turns negative. If they tell you right away it's a decay problem, then just make that negative. Any other questions? We have about 5 minutes left. Also, don't forget, if you were going to retake the quiz, that you need to do that today. Otherwise, I'm putting the grade in the grade book for next week's eligibility.